All right, so we have here a slightly more complicated circuit. It's in fact a couple of three resistors wired in parallel, and then those three resistors are in series with another resistor. So we have a parallel tucked into a series circuit. Okay, it's nothing to get intimidated by necessarily. Just follow the same steps and guidelines that I have up here and you should be just fine. So have Ohm's law equations available. Okay, again, these are going to be pretty important. V equals I times R. I is equal to V divided by R, and R is equal to V divided by I. And then finally, we're going to need at the end, P is equal to I times V. Givens. We have 5 of them. All right, so once we figure out where those go, we'll have all the givens. Total voltage coming out of the battery, coming from the battery, I guess, is going to be 20 volts. We have our first resistor. Again, I like to typically just go clockwise unless I absolutely need to go the other way, so I'm going to go clockwise. We have our 50 ohm resistor for our first one, 50 ohms. And then when I get to this point, I'm just going to go left to right. So 16 ohms, 16 ohms, and 8 ohms. All right, so that takes care of our givens. We got all 5 taken care of and in our chart already. All right, so we got a big chunk. We know power is going to take care of itself at the end, and so we are what, a good third of the way through, and we barely had to do anything. Nice and simple, right? So look for easies. Well, easies are if you know the current in a series circuit, then you know the current in every resistor. So if we knew the current at either the 20 volt battery or the 50 ohm resistor, we know that the current for those are going to be the same. All right, that's one of the easies. The current is going to be a big mess when we get down here. It's going to split up 3 ways, but between the 50 ohm resistor and the battery, we know that the currents will be the same. We don't know the current at either one, so we got to skip that for now. We also know that the voltage drop for each branch will be the same for this parallel part here, these 3 resistors wired in parallel. But we know we're going to start at 20 volts, but we don't necessarily right now know how much. We don't know how much voltage we're going to drop at the 50 ohm resistor, and so we don't know how much voltage will drop here. So we don't have any easies yet, is what I'm trying to say. So let's do some calculations. Well, the only calculation we could do is to figure out the total resistance. And to be honest, this might be one of the harder parts if you're still not super comfortable with this. Because we can't just add them up and we can't just do inverses. We had to do the combination here. So what I do know is that I got a 16 ohm resistor, got a 16 ohm resistor, got an 8 ohm resistor, and got a 15 ohm resistor. What's the total? Well, whenever you have a situation where you have in this case, we have a series circuit on the outside and we have sort of like this parallel part embedded inside of it, then I just like to work my way from the inside out in these types of situations. So what I'm going to do is I'm going to figure out the total equivalent resistance of this part right here of these 3 resistors. What's the total equivalent resistance here? So what I'm going to do is I'm going to do the inverse of 16 plus the inverse of, it's a negative, of 16 plus the inverse of 8. Saying what I'm typing and writing what I'm saying, it doesn't go very well. So let me just make this super clear. This is supposed to be a negative and this is supposed to be a 1. So I'm going to redraw that just to make sure that everything is clear. So this is an inverse of 16. This is an inverse of 8. Okay, so I'm going to add those together. I'm going to take my calculator and I'm going to do 16 inverse plus 16 inverse plus 8 inverse, and I get 0.25 for my answer. So then I had to take the inverse of that. So the inverse of that, my answer is going to be 4. So that's going to be my total resistance for this part right here. So all 3 of these resistors together, the total resistance is going to be 4. And again, my clue that I'm correct is that it's the 4 ohms is less than the smallest resistor of the part of this section right here that I'm figuring out. So I'm pretty confident that I did this part correctly because of that. Now, this part right here is in series with this 50 ohm resistor right here. So now I could just add those together, and I know that my total resistance is 54 ohms. So I was able to calculate that first because of all the resistors. Okay, there's still no easies I could do, so I had to do another calculation. And because of that, because of what I just did, I'm able to now figure out the current coming out of the battery. And so I is equal to V divided by R. So I'm going to take 20 divided by, let's see, 20, I don't have to write this here, 20 divided by 54. And so V divided by R, 20 divided by 54. And I'm going, 20 divided by 54 gives me a decimal. So I'm going to have to round it a little bit, 0.37 amps coming out of that battery. Okay. So coming out of this battery is 0.37 amps. Now we finished another step. So at each step, look for these. So I'm going to go, are there any easies? Well, like I said at the beginning of the video, if we knew the current at either the battery or this 50 ohm resistor, then we know the current everywhere in the other one. So because of this, I know that the current going through the 50 ohm resistor is 0.37 amps. Okay, we got another one. That current, that 0.37 amps, is going to continue down through the wires, and it's going to split up into 3 ways here. And then the cool thing is, the total current going through these 3 things is also going to be 0.37 amps. It's just going to be divided up somehow. We don't know exactly how it's going to be. So we got to stop there. We cannot say these are going to be 0.37. We know the total of these 3 will be 0.7, but each one is going to be a lot less than that. So what do we do? Well, we got another blank here. Whenever we got V or I or R, we got 2 of those 3. We could figure out the third one. So let's do that. So I'm going to take my little arrow to indicate. See this little path we're following? Excuse me. Well, voltage. This is why I write down all 3 equations. Voltage is I times R. So I'm going to take that 0.37. I'm not even going to round that. I'm just going to hit multiply. So if you start rounding things, your answers might be slightly different than me. So I'm not going to take 0.37. I'm going to take what actually is in my calculator, which is 0.37037037004. Whatever. I'm just going to hit that times 50 ohms. And that gives me a voltage of 18.5 volts. Okay. So, great. Now what? We know that the voltage drop from here to here, let's put a little arrow, is going to be 18.5 volts. Well, now what? Okay, this is sort of an easies, except it's not. You just have to, by easies, like I said earlier in another video, easies is using the rules of circuits to your advantage. Okay, knowing that the current going through one thing in a series will be the current going through all the things in a series. The rules of a parallel note, meaning that you know that the voltage drop across one branch will be the voltage drop across every branch. So what I could do from this, because I can't calculate anything, I can kind of, but what I know is that the voltage from here to here is going to be whatever's left over after it drops 18.5 volts here. So we're going to start at 20 volts. We're going to lose 18.5 volts right here. So that means we're going to lose another 1.5 volts from here to here. So that means that, and it doesn't matter which branch you go down, just like you take the elevator to the top of the stairs in a hallway, you walk down the hallway, you go down some stairs, and then you're now on another floor, you take another hallway, and the hallway splits up 3 ways, and no matter which way you go, you're going to find a stairwell that goes down the rest of the way. It's going to go down 1.5 volts no matter what. So from here to here is going to be 1.5 volts because that's how a parallel, things wired in parallel works. All right, that's supposed to be a dot. So that's our quote unquote easies. I know it's not super easy, but that's using the rules of circuits in a way that helps us out. Well, that leaves one blank. I mean, we're not counting power because, that's going to come later. So we just have to find current. So we take our 1.5 and we divide it by 16. Okay, current is voltage divided by resistance. So 1.5 divided by 16 gives me, that's a small number. So let's say 0.94 amps. Oh, you know what? I got to squeeze another zero in there. 0.094 amps. 1.5 divided by 16 is going to give me another 0.094 amps. And 1.5 divided by 8, is going to be 0.1, call it 19 amps. Okay. So I said earlier the current here, just to double check, the current here, when you splits up three ways, should equal the 0.37 amps. So if we do the 0.19 plus the 0.094 plus the 0.094, 0.378, yeah, I mean, basically, because we rounded, so we're not going to get the same exact. So we're going to have some rounding issues there, but it works out. Okay, and I got that because, well, let's just kind of plot our course here. We figured that out, and then we were able to go from there to there. I'm just drawing arrows just for this demonstration to show the path we took. Okay, so we started with the summing of the resistors. We were able to calculate the total current. Calculating the total current, we knew that the current going through the other resistor was the same. And then from there, we figured out the voltage drop at that resistor. And then from there, we could figure out the voltage drop across all the rest of the resistors. And then from there, we were able to calculate the current going through each of those resistors. So it's a little puzzle, a little game to play with the math. But I think it's, hopefully something you could handle after a little bit, after some practice. So power. Power is I times V. So 0.37, I'm just going to round for this one, times 20 gives me 7.4 watts. 18.5 times 0.37, I times V, or V times I, gives me 6. We'll just call it 8 watts. It's actually 845. I times V, so 0.094 times 1.5 gives me 0.14 watts. And then we're going to get the same answer for this one, 0.14 watts. And for this one, we should get twice that, but I'm going to just double check, 0.19. So my current times 1.5, yes, good, 0.2. We got to round that one up. Okay. So do these add up? 0.29 plus 0.14 plus 0.14 plus 6.8. Does that all add up to 0.74, 7.4? Close enough. Yes. I mean, because of our roundings we did, we're not going to get the same exact, but it's close enough to show that we did it correctly. So that's it. Don't be intimidated. You saw how long that took. Just follow the steps, follow the general guidelines, and you should be fine.